Now we discuss liquid junction potential. So liquid junction potential is the voltage difference that develops at the interface where two electrolyte solutions of differing concentrations or compositions come into contact. This happens because ions in each solution diffuse across the junction but at different speeds depending on their individual mobilities. When two solutions touch, their ions begin to migrate from areas of high concentration to low concentration. However, if the cation and anion have different mobilities or speed, one may diffuse faster than the other. For example, if the anion moves faster, the dilute side becomes temporarily negatively charged and the concentrated side positively charged, creating an electric potential difference across the junction. This separation of charge leads to development of the liquid junction potential, also called the diffusion potential, which is a non-equilibrium phenomenon. So the mathematical expression is, so ELJP is LJP stands for liquid junction potential, is EWT minus EWOT, and we know this expression LJP will become now 2T minus RT by F ln C2 minus C1. This is for EW2 that we already discussed, minus RT by F ln C2 by C1 for EWOT. So if we rearrange, we get 2T minus 1 times RT by F ln C2 by C1. Next we discuss potentiometric titration. Potentiometric titration is a laboratory method to determine the concentration of a given analyte. In this method, there is no use of chemical indicator. Instead, like acid-base titration, normal titration, we usually use indicators like phenolphthalein, methyl orange, etc. Here, instead, the electric potential across the substance is measured. Potentiometric titration involves the use of two electrodes, an indicator electrode and a reference electrode, commonly a hydrogen electrode or a silver chloride electrode. The indicator electrode forms one half cell with the ions present at the analyte solution, which acts as the electrolyte. The reference electrode constitutes the second half cell, providing a stable and known potential for accurate measurement. So potentiometric titration is generally divided into three categories. First is acid-base titrations, second is oxidation reduction or redox titration, and third is precipitation titration. So first we discuss acid-base titrations. In an acid-base titration, for example HCl versus NaOH, the electromotive force or EMF of the solution is measured by immersing an electrode that is reversible to hydrogen ions into the given volume of the acid solution. The electrode is coupled with a suitable reference electrode to form a complete cell. The change in the electromotive force or EMF is measured with each addition of a base as the pH of the solution changes. At 25 degrees Celsius, the relationship between the potential and pH is given by E naught is 0.059 and pH at 25 degrees Celsius. Okay, so here the schematic plot of E versus volume of analyte added. So you can see if this side volume of titrant increases and this size E we are measuring here. Now initially you see there is no change in the EMF value, okay, as we increase the titrant, okay, titrant amount here. As we keep on adding a titrant amount, so EMF does not increase much, but after this point there is a sharp increase here in the EMF value, and then if we still keep on increasing, keep on adding titrant, there is almost no change in the EMF value. So this is the mid. If we draw one line here like this is the midpoint. So this is the equivalence point here. Okay, so corresponding to the volume of this equivalence point, we can actually calculate how many, what is the concentration or of titrant or volume of titrant is used. The equivalence point is the stage in a titration where the amount of titrant added is chemically equivalent to the amount of analyte present in the solution, like in normal titration. At this point, the reaction between the titrant and the analyte is stoichiometrically complete, resulting in a sudden change in potential, like here as I mentioned, which is observed as a sharp jump in the titration curve. In potentiometric titrations, first and second derivative graphs are used to determine the equivalence point more accurately. So this is the first derivative, okay, of equivalence point here. Okay, so this is the point where equivalence point has been reached here. Okay, this is the volume required. The first derivative curve delta E by delta V versus V shows a sharp peak at the equivalence point, indicating where the potential changes most rapidly. Okay, you can see the potential changes most rapidly here. The second derivative curve delta 2 E by delta V raised to the 2 versus V crosses 0 at the equivalence point, providing a precise and objective way to locate it. So if we plot the second derivative of potential here with respect to volume, so we can actually calculate equivalence point. Especially useful when the main titration curve is not sharp or has a multiple endpoints. So these two methods, okay, the first derivative and second derivative, they are mostly used when the equivalence point is not very sharp or there are multiple equivalent points. Then we move to oxidation reduction or redox titrations. In redox titrations, the electrode that is reversible to hydrogen ions is replaced by an inert metal electrode, typically platinum, which is immersed in a solution containing both the oxidized and reduced form of the same species. This electrode functions as an oxidation reduction or redox electrode. So, see, if we consider a redox reaction like ferrous ion Fe2 plus Ce4 plus cesium, Fe2 plus Ce4 plus gives Fe3 plus Ce3 plus. So this is a redox reaction. Here iron is getting oxidized from +2 state to 3 state here, and C is getting reduced from +4 state to +3 state. So the Nernst equation is, so if you consider the Nernst equation, so E electrode will be E naught electrode plus RT by F ln Fe3 plus by Fe2 plus here. Okay, and then if we substitute the values of RT by F at 298 K, so we get this expression E naught EL minus 0.059 log of Fe3 plus by Fe2 plus. So in the ratio, if the ratio of this concentration is 0.01, then we get EL is E naught EL minus 0.1182. So at the equivalence point, concentration of Fe2 plus and C is equal to concentration of C4 plus, right? So you go back and check. So at the equivalence point, so concentration of Fe2 plus and CO4 plus, they are equal. Similarly, concentration of Fe3 plus equals to concentration of Ce3 plus. So we can write at equivalence point, E equivalent is E1 naught plus 0.059 log Fe3 plus by Fe2 plus equals to E2 naught. This is for C, okay, so 0.059 log Ce4 plus by Ce3 plus. So at equivalence point, okay, so we get E naught, E1 naught plus E2 naught by 2. Next we discuss precipitation reaction. A precipitation potentiometric titration is a type of titration in which the endpoint is detected by measuring the electromotive force of a cell as a precipitation reaction occurs between the titrant and analyte ions. Instead of a visual indicator, the potential change between a reference electrode and an indicator electrode is used to determine when the precipitate formation is complete. Now consider we are taking one example. So consider the precipitation of potentiometric titration of chloride ion with silver nitrate, where the key reaction is Ag plus Cl minus gives AgCl. Okay. As the indicator at the indicator electrode, the equilibrium is Ag is in equilibrium with Ag plus. According to the Nernst equation, the potential of the silver electrode will be EAG, if we say, so equals to E naught AG plus 0.059 log concentration of AG plus, because this concentration of AG solid is 1, so at 25 degrees Celsius. So from the solubility of equilibrium of silver chloride, we know that AgCl ionizes as Ag plus Cl minus. So the solubility product constant Ksp is concentration of Ag plus times concentration of Cl minus. So from there actually we can calculate concentration of Ag plus. So concentration of Ag plus will be Ksp by concentration of Cl minus. Now if we substitute the concentration of Ag plus from here to this equation, so if we use the Nernst equation, we get Eg equals to Eg naught plus 0.059 log Ksp by concentration of Cl minus. So if we rearrange this equation, we get Ag equals to E naught Ag plus 0.059 log Ksp and minus 0.059 log concentration of Cl minus. Now this quantity E naught Ag plus 0.059 log Ksp, because Ksp is a constant term. So if we consider this one as E prime, so we write E equals to E prime minus 0.059 log of concentration of Cl minus. Now if we see, if we keep on adding AgNO3, so value of E increases here, okay, and then here we get sharp increase, okay. So here this is the equivalence point, okay. So this is this volume we can now measure, okay. And then after once the precipitation is completed, there is not much change in the E value here, okay. So from there actually we can calculate volume of AgNO3 from the equivalence point. The equivalence point is when moles of Ag plus added equals to moles of Cl minus present. The solution of saturated with AgCl and both ions have equal minimal concentration given by square root of Ksp, right. So you can see this is square root of Ksp, okay. So since the concentration of Ag plus and Cl minus are the equal, okay. So after the equivalence point, all chloride ions have precipitated as AgCl, right. So if we keep on adding AgNO3, we get some change because of the presence of excess Ag plus and NO3 minus. Now we discuss a few problems. The first problem is 0.05 molar NaOH solution offered a resistance of 31.6 in a conductivity cell at 298 K. If the area of the plates of conductivity cell is 3.8 centimeters square and the distance between them is 1.4 centimeter, calculate the molar conductivity of the sodium hydroxide solution. So value of A is there, okay. So is given, okay, area of the plates, okay, and the length L is also given. So L is 1.4 centimeter and A is 3.8 centimeter square, okay. So given the area of the plates, A is 3.8 centimeter square, okay, and the distance between the plates if we say this is L, so we write this is 1.4 centimeter, that is also given. Right. So we can calculate cell constant, therefore cell constant, we already discussed what is cell constant. So cell constant is L by A. So we put the value of L and A here, 1.4 by 3.8, and this is centimeter and this is centimeter square. So we get the cell constant value is 0.368 centimeter inverse. So this is the value of cell constant. So resistance is given 31.6, this is ohm, okay. So we can write, so the resistance omega is 31 point, resistance R is 31.6 omega, okay. And what else is given here? Here the concentration is given, okay. So the concentration the concentration of NaOH solution, if we call it C, is 0.05 molars, right. So, the conductivity K, so we know the conductivity K or kappa, rather conductivity kappa is cell constant times conductance. So, cell's constant value we know 0.368, okay, and conductance is nothing but 1 upon resistance times 1 by resistance R. Okay. So, we get 0.368 by the value of R we know 31.6. So, we get the value is 0.0116 S centimeter to the minus 1. So, this is the value of the conductivity. Now, the molar conductivity, because we need to calculate the molar conductivity, molar conductivity of the sodium hydroxide solution we say this is lambda m is K or kappa times 1000 by C, right. So, kappa you already got 0.0116 times 1000 and the concentration C also we know 0.05 molar. So, if we calculate this one we get 232 S centimeters or mole inverse. Okay, so, this is the value of the molar conductivity of the sodium hydroxide solution. Next, we move to problem number 2, which says resistance of a conductivity cell filled with 0.1 molar KCl is 100. Okay. If the resistance is 100 ohm. Okay. So, if the resistance of the same cell when filled with 0.02 moles of 0.02 m KCl solution is 520. Okay. So, calculate the conductivity and the molar conductivity of 0.02 molar KCl solution. So, conductivity of 0.01 m KCl solution is also given 1.29 S m to the minus 1. So, given here the resistance of (0.1 m KCl), if we call this is R1, is 100 ohm. The conductivity of (0.1 molar KCl, if we call this as kappa 1, is 1.29 S m inverse. Okay. So, we know that kappa is G times L by A, okay, or we can write here G1 here. So, G1 is 1 by R1, right. So, resistance is of 0.1 molar KCl if we consider R1. Okay. So, this is now we substitute this. Okay. So, we get L by A is kappa by G1. So, we can calculate we got L by A or the cell constant value. Okay. So, we get 1.29 S m inverse, okay, times 1 by G is R1, right? So we now write L by A is 1.29 S M inverse, and the value of R1 is 100 ohm. Okay, so we get 129 M inverse. So we get L by A is 1.29 centimeter inverse. Okay, so this is the value of the cell constant. This is the value of cell constant that we calculated, because we will be using the same cell here. Okay, it is same cell. So we need to calculate the cell constant first. Okay, now to calculate the conductivity of or the conductivity of .02 molar KCl, if we say this is kappa 2 is G2 times L by A. So now we got the value of L by A, and G2 is nothing but R2. So R2 is given. Okay, so the resistance of 0.02 molar KCl solution, if we call this R2, is 520 omega. So kappa 2 is 1 by R2 L by A. So we can calculate the value of kappa 2. So 1 by R2, okay, so 1 by R2 means 1 by 520, and the value of cell constant is 1.29. Okay, so if we calculate this, we get the value of kappa 2. So kappa 2 is 0.248 times 10 to the minus 2 S centimeter inverse. So this is the value of molar, this is the value of conductivity of 0.02 molar of KCl solution, kappa 2. And we need to calculate the molar conductivity also. So now the concentration is, so in order to calculate molar conductivity, we need to know the concentration. Okay, the concentration of 0.202 mKCl solution, if we say this is C2, is 0.05 m, right. So we got K2, we got C2. Now we can easily calculate lambda m. Okay, therefore the molar conductivity of .02 m KCl solution, if we say this is lambda m, is K2 times 1000 by C. The value of K2 we already calculated, this is 0.2, this is C2, 0.248 times 10 to the minus 2, and the value of C2 is 0.05. So if we calculate this one, we get 124 S centimeter raised to the 2 mole inverse. So this is problem number 2. Next we move to problem number 3. It says a potential difference of 20 volt applied to the ends of a column of 0.1 molar AgNO3 solution, 4 centimeter in diameter and 12 centimeter in length, gave a current of 0.2 A. Calculate the conductivity and molar conductivity of the solution. So according to Ohm's law, we know V is IR, right. We know V is I times R, so it gives R is V by I. So here V is potential difference, so V is 20, so this is 20 volt, and current is 0.2 ampere, so 0.2. So if we calculate this one, we get 100 ohm. So this is the value of R, resistance we have got. Okay, so R is the resistance. So value of resistance we have got. Now diameter of the column is is 4 centimeter. Therefore, the radius of the column is if we say this is R is 4 by 2 equals to 2 centimeter. So we got radius of the column. Now we can calculate the area of cross section, right? Okay, so area of cross section of the column so if we say this is A, this is nothing but pi r raised to the 2 centimeter square here. So we got 3.14 times 2 square. So if we calculate this, we get 12.57 or 56 rather here, 56 centimeter square. So this is the value of area of cross section. Okay, now the length is also given, right? Length L. So length of the cell, length of the column, the length L is given, L is 12 centimeter. So we can now calculate cell constant, right? So cell constant is L by A, so 12 by 12.56 centimeter inverse. So we got the cell constant. Now we can easily calculate the conductivity. Okay, so the conductivity kappa is G times L by A. So G is 1 by R, so 1 by R times L by A. So value of R we have already got and value of L by A we got. We put that, so times 1 by 100 times 12 by 12.56. So if we calculate, we get 9.55 times 10 to the minus 3 S centimeter inverse. So we calculated now conductivity. Now we can calculate molar conductivity because the solution concentration of the solution is given. The molar conductivity lambda m is kappa times 1000 by C. Now the concentration of the AgNO3 solution C is given 0.1 m. So we substitute everything. So we get 9.55 times 1000 by C is 0.1. So if we calculate this, we get 95.5 S centimeter to the 2 mole inverse. Okay, so this is the value of the molar conductivity. Okay, S centimeter inverse and centimeter square mole inverse.